All right.
Yes, go.
Okay. Let's get started. So today it's our great pleasure to have Heng from University of Bern. Kevin did his undergrad at National University of Singapore, and he went to graduate school in University of Colorado Boulder and got his PhD in 2007. He then moved to Institute for Advanced Study, first as a member and later as a Frank and Peggy Taplin member, and later and in 2010 he moved to ETH Zurich as a Zwicky fellow, and in 2013 he joined the faculty at Center for Space and joined the Habitability, yes, at University of Bern as assistant professor, and he was promoted as a full professor in 2015. And last year, he became director of Center for Space and Habitability. Kevin has developed extremely broad research interest over the years. When he was doing his PhD, he was mainly working on something called Balmer-dominated shocks applicable to supernova remnants. And since his postdoc, his research interest substantially broadened, and especially he moved into this area of exoplanets. He has developed interest in fluid dynamics, planet formation, brown dwarfs, and especially he's now primarily working on many areas in exoplanet atmospheres. Kevin has also recently published a book on the exoplanet atmospheres, theoretical concepts and foundations. And so today he's going to talk about radiative transfer in exoplanet atmospheres. Thank you.
Thank you for the very kind introduction. Thanks for having me. Could I have a laser pointer?
Oh, yeah.
So I realized that the title of the colloquium is a little bit specific for colloquium, and I'll try to motivate it to make it interesting for you. So this is what I'm going through today. I would like to talk a little bit. I would like to do a brief review. I'll make it as clear as possible about the radiative transfer equation and solution strategies. I would like to tell you something about two-stream radiative transfer and why you should care. Then I would like to tell you a result that we're very excited about because it improves upon a standard method that has been standard for about 30 years. And then I'm going to tell you why it matters using the case of early Mars. So this is the cartoon slide that motivates why you should care. So in the field of exoplanet atmospheres, we would very much like to measure spectra and interpret spectra. So as a theoretician, I would like to set up a model atmosphere in which I irradiate the atmosphere with starlight. My model atmosphere has a discrete number of layers. Each layer has its own temperature and pressure, and therefore I can construct a cross-section of the opacity of each layer. I can construct the optical depth, and then I can dilute the starlight as a function of wavelength down. The type of the star is important because, say, an M star versus a G star, you would have the energy being distributed across wavelength differently. You would have different UV radiation energies and so on. And this affects how you absorb starlight as a function of depth, and it affects the ionization fraction of different metals high up in the atmosphere. So you have to do all that. You have to deposit the starlight, and how each layer absorbs depends on the chemistry of each layer. So the temperature and the pressure and the elemental abundances will tell you what types of molecules, how much CO do you have, how much H2O do you have, and how much methane do you have, and so on. You also have to worry about the boundary condition at the bottom of the atmosphere. This may be a heat flux, but in a more general sense for exoplanet atmospheres, this may be a chemical flux or biological flux. So you have to worry about the initial conditions. You have to find a way, and this is the point of the talk, you have to find a way to, for a given pair of layers, you would like to have a method that teaches you how to transfer flux from one layer to the other. And the reasoning is that if I can do this for a pair of layers, I can do it for an arbitrary number of layers. And when I can do that, I can iterate that with the chemistry and energy balance, and I can get a fully self-consistent atmosphere that I can compare to observations. This is the goal.
Your plot here is one-dimensional, but in reality you have day side, night side, there could be winds in the other dimensions. Can that be neglected?
Absolutely. That's a different talk altogether, and I'm fully aware of all the caveats, but I'm trying to, the point of this talk is to point out that even in one dimension, you have all of these subtleties and caveats that you have to worry about. So for the rest of the talk, I will pretend that these things are plane parallel in 1D. But as you will see, even in this approximation, things are not that simple. So there are different ways to specify solutions for fluxes going from one layer to the other. There's a method that's very old. It goes back to the earliest paper I could find on it was in 1905 in the Astrophysical Journal. This is the two-stream method. The two-stream method works when the atmosphere is so thin that the vertical dimension of the atmosphere is much smaller than the horizontal dimensions. So you can pretend that the fluxes passing through the atmosphere go up, just up or down, roughly speaking. Mathematically, it's not quite true, roughly speaking. And there have been a number of really nice papers on it. And if you're interested in this topic, I encourage that you read these papers. So the paper by Meadow and Weaver in 1980 is the paper that really started to put it all together as a theoretical exercise. Toon et al. Is a very influential paper in the planetary sciences, has been used a lot. And Toon et al. Is the two-stream method that is used in all of the codes by Jonathan Fortney and Mark Marley, if you know these people. I particularly like, well, for more, before I talk about the earlier papers, I also worked on it in a paper in 2014. This is covered in the book by Ray Piambe, who is a climate scientist who now also works on exoplanets, and in my own book as well, which came out this January. I will talk about this book during the lunch talk, so if you have time, stick around, and during the 15-minute lunch talk, I will talk about this book and also give away a free copy to a student. But back to the topic, which is, I really like these two earlier papers in 76 and 77, because they tell you about an old problem that's been outstanding for a while, which is that these two-stream solutions are really inaccurate when you're treating large aerosols in the atmosphere. And the reason why you care is because the observations seem to suggest that some non-negligible fraction of exoplanet atmospheres are cloudy, and cloudy atmospheres are difficult to interpret because your interpretation of the chemistry in the atmosphere is degenerate with the properties of the clouds. So you would like to have a method that handles the presence of aerosols accurately. I would like to show you, it's usually bad form to read from a slide, but in this beautiful paper in 77, he says it so well that I would just read two sentences to you. I couldn't have said it better. So the first sentence is, the difficulties of performing radiative transfer calculations for strongly asymmetric phase functions, which are true for medium to large aerosols, compared to the wavelength that you're scattering the light at, are too well known to need belaboring.
What does phase function mean?
I will tell you.
Okay.
I will describe this to you first, and then I'll spend the next few slides telling you what these words mean. A direct attack on the problem, a brute force approach, can consume enormous amounts of computer time and storage space. Surprisingly, these two statements are still true today, still very true. And then he goes on about how there's a whole literature on how to deal with this phase function, which I'll talk about in the next few slides, and these involve brute force techniques like series expansions and so on and so forth. They don't work very well, and they consume a lot of computer time. Now, let me tell you about these.
Can I interrupt for a second?
Sure.
Just to ask, I'm not familiar with planet atmospheres at all, but in stellar atmospheres or other radiative transfer calculations in 1D, the two-stream approximation that people developed involves effectively solving the radiative transfer problem among one ray and picking the orientation of the ray such that you get the correct flux.
I'll talk about this.
But is that different from this?
I will talk about that, and I'll talk about why there's a misunderstanding about that direction. It's actually not a direction, and I'll tell you why.
Okay, I'm curious now because...
yeah, just wait for the slide.
Just as a follow-up on that, what you described is the atmosphere being thin compared to the other scales in the problem curvature, etc.
Absolutely.
Is a validation of 1D, but it's not a validation of 2-stream in general.
What do you mean by validation of two-stream? Just to say a bit more.
Just so you're making an approximation, and the reason that you stated justifies the 1D approximation, but it doesn't necessarily justify.
So I will show you calculations towards the end of the talk where our two-stream solution matches the 32-stream calculation.
Okay.
But in order to get there, I need to explain all this background. So let's talk about the radiative transfer equation. So in plain English, what it tells you is the rate of change of intensity through a medium where the correct length is the optical depth. Think of the optical depth as a dimensionless length. Is the contribution of the intensity minus or plus whatever is due to scattering and a black body contribution term. Whether these terms are minus or plus depends on your convention on where you put the 0 point of the length and which direction it increases in. So it could be minus or plus. The minus and plus is not so important in these terms. This is the scattering phase function. And the reason why this is difficult to solve, as I will tell you in the next 1-2 slides, is because this scattering phase function describes how the intensity impinges upon the medium and escapes the medium. So it describes the change in angle of intensity as it passes through the medium. And you have to multiply this by the thing that you're solving for in the first place and integrate over all of the outgoing angles. So this is in general not something that's easy to treat. Let me show you what the other quantities are first, and then I'll talk more about this. So this is the cosine of the angle, this is the optical depth I already talked about, this is the intensity, this is the scattering phase function, the Planck function. This important quantity is called the single scattering albedo. It's the ratio of the scattering cross-section to the scattering plus absorption cross-section. So it's a measure of how strong scattering is in one event. So in pure absorption, this would be 0, and this term would go away. And this would be 0, so you have just black body. And in pure scattering, this term would go away, right? And so I found it helpful, or at least when I teach a class on this, to think of it as microscopic and macroscopic quantities. So I tend to think of the single scattering albedo and the phase function as microscopic quantities, and the rest as macroscopic quantities.
Stimulated emission is part of this or not?
No, it's not part of
You
this.
don't have stimulation.
There are some assumptions taken with this. Stimulated emission is not part of this, and this is the time-independent version of the radiative transfer equation. There's a time-dependent version, which I'm not talking about. So back to the phase function that we had questions.
That's absorbed into the opacity.
Yes, it is. It's absorbed into K.
Well, it's negative. It should be negative.
But if it's
Absorbed.
done correctly, that's how
Why?
they should have the correct, the absorption coefficient should have stimulation in it.
That's one there. Yes, it's
Yeah, this is something we don't treat in the planetary atmosphere, so you think about it.
it's incorporated.
It's incorporated.
Okay. So this is the interesting part of the equation that drives the rest of the talk, right? This term is difficult to evaluate, as I said. There are different strategies, and you can think of these strategies in a unified framework, if you will. There's a strategy due to Chandrasekhar called discrete ordinates, and the basic idea is that you would expand the scattering phase function in a basis function in a basis series of Legendre polynomials, and the series can be as long as you want. And then this integral itself is itself a series. So you have a series within a series, and then there are papers in the literature devoted to how many terms in each series you should take and what the conversion properties of that are. It's messy. There are also papers that deal with the fact that when you have large aerosols, most of the scattering of the radiation is peaked in the forward direction. So some people have invented methods where they take the scattering phase function and they decompose it into a bunch of terms and a delta function. Then there's a whole discussion of where should I cut off the delta function and how should I renormalize things and so on. It's a little bit ad hoc and it's messy and it takes computational power. And this is not what we're going to do today. But I wanted to mention its existence to you. The second method is two-stream. And what two-stream does is two-stream says, let's circumvent this term. Instead of solving the equation as a function of optical depth or normalized length and an angle, let's integrate the whole thing analytically and integrate out the angle. So you're left, instead of a partial differential equation, you're left with an ordinary differential equation just in the optical depth. This is what two-stream does, and I will spend some time in the talk talking about this. There's a hybrid method by Toon et al. Called the two-stream source function method. And the idea behind this method is they play a trick. So they say that let's take the two-stream solution and let's pretend that the intensity is the flux divided by some mean angle. And then let's shove that solution into this thing in the integral. And let's guess a functional form for what the scattering phase function is. And this allows me to integrate this. So it's no longer an integral. Evaluate this. And then I can evaluate the whole thing as ODE. This is the method that's used in Toon et al. And this is the method that is used in all of the codes that Jonathan Fortney and Marley publish in their papers when they do radiative transfer calculations. So let's talk about two-stream. So remember, two-stream is instead of solving for the intensity, I would like to integrate over the angles. So I take moments of the intensity. And what I mean by that is you take the intensity and you integrate over all angles, and you integrate the intensity weighted by different powers of the cosine of the angle. So the 0th moment is the total intensity, and the first moment is the flux. Right, so when you do this exercise, what you find, and I won't show you all the details, what you find is that, as I mentioned, you end up with one differential equation that depends only on optical depth. The problem is that you end up with a situation in which you have always one more unknown than the number of equations. So the system is mathematically underdetermined. And the way that people get around this, and this is, stretches back to the earliest papers, is that they pretend that the ratio of these moments are constants. And the ratio of these moments are called Eddington coefficients. And that's related to your question that I will answer in the next slide. So these are the Eddington coefficients that go into the simplest version of the two-stream. There are more complicated versions. And the first Eddington coefficient is the total flux divided by the intensity in both hemispheres. The arrows simply show you the hemispheres. So am I integrating from 0 to 180 degrees or 180 to 360? Just think of one outgoing and one incoming hemisphere. And subsequently I will argue to you that the value of this Eddington coefficient should be half. Some people like to think of this as an angle. So some people think of this as a flux divided by the intensity equal to some characteristic cosine of the angle. And that the characteristic cosine of this angle is half. I find this to be very misleading because it's not an angle.
I agree with you, and actually that's not what, this is not called the two-streams, that the approximation is the Radiative spheres.
I understand.
This is called the variable Eddington factor approximation. That's why I'm saying, or like the fact, I think it's just the terminology difference. So when I was talking about the two-stream stability and the cosine of the angles, is that you prove it in a different way.
Or no, square root.
Exactly, yeah, that's right. You prove it in a different way. Whereas this one, I completely agree with that, is a half. And actually, you shouldn't be doing the epsilon prime as outgoings and ingoings simultaneously because we actually have no idea what that number is. It's only the average of the two that you have, the prime, and what that number is. But it's just a terminology difference.
Right. So
normally in radiative transfer, that's not what you would call the two-stream approximation. And
you could call it the variable Eddington factor.
For
other audiences.
My response to you is that there's no consensus in the literature on what's called two-stream.
I was just trying to understand that.
And in the planetary hemispheres literature, we call this two-stream. And the reason is because I can derive the values for all the Eddington coefficients self-consistently from first principles within one framework. This is what is shown in the book. I can do that. I don't need to do arbitrary series expansions. It's all first principles. This is why...
Independent of the radiation.
Sorry?
Independent of the radiation.
I can show you the book later. We can talk about it. I've gone through this derivation many, many times. Go ahead.
Isn't this value of epsilon less a mean angle and more just the first Gaussian quadrature coefficient?
I don't know what you mean by that.
Like if you do the discrete ordinance derivation in the two-stream case, that coordinate epsilon of the mu1 in the literature is also just the first moment of the Gaussian quadrature approximation.
It could be, but it doesn't need to be for you to set its value, which is what I will tell you.
Right, but it's the best one.
In terms of what? Setting the value?
In terms of if you have a one series expansion, which is what you're doing in two-stream, the Gaussian quadrature theorem says that that value of a half or 1/3, depending on if you're doing single or double quadrature, gives you the single best guess if you plug in a value of mu1 there.
Sure. That's fine. I mean, it doesn't change anything I'm going to tell you. It's fine. So what I'm going to tell you later is that it's reasonable to set this to half. It's not reasonable to set this to whatever value is set commonly in the literature. And when you stop doing that, you get a very you get a solution that has a greatly improved accuracy. This is what I'm going to tell you. So when you do the two-stream, in the way that is defined in the planetary science literature, what you end up with is, the reason why I don't think of these as angles, those Eddington coefficients angles, is the following. It turns out that when you do the derivation of the equations, it's useful to think of a normal optical depth going from top to bottom and a slant optical depth that is related by some characteristic cosine of the angle. The reason why you do that is a mathematical bookkeeping trick. You're just trying to keep track of minus signs. So this is why it's tau prime and not tau. And once you do that, once you get the minus signs out, this thing is reabsorbed back into this slant optical depth and makes it the normal optical depth again. So this is just a bookkeeping trick to tease out the minus signs. Whereas in the literature, you find often people quoting values for what the cosine of this angle is, and this is something I disagree with. But the structure of the two-stream equation goes as follows. You have two equations and two unknowns. You have the flux going up and the flux going down, and you have three different terms. One is transmission, this is absorption, and this is blackbody radiation. And the reason why I labeled it A, S, and B is because this is absorption, scattering, and blackbody. Right? So you can solve this pair of equations. It's just a pair of ODEs. But the detail that's important is that hidden in these coefficients are these Eddington coefficients. And how do we fix the values of these Eddington coefficients? And this was done in the '89 paper by Toon. So there were two lines of reasoning. The first line of reasoning is that in the opaque, purely absorbing limit, you should get pi b of flux in each hemisphere. And when you do that, you get half for this Eddington coefficient. So this is a reasonable constraint. Let's keep this. The second limit that Toon et al. In '89 discussed is that in the pure scattering limit, the system should be in radiative equilibrium. Radiative equilibrium is a statement of local energy conservation. It means that the flux between the gradient of flux between each layer, each pair of layers in the atmospheres is zero. In Toon et al., this was enforced, but I find this to be an academic constraint because there's no reason that, I'm sorry, let me say it again. I find it to be an academic constraint because this only works in the purely scattering limit, and in practice you never quite reach the purely scattering limit. And so you're enforcing a condition that you don't really use. So the idea is, let's try and relax this and generalize this. And I'll tell you about this in the subsequent slides.
Radiative equilibrium, astronomer, we will teach a class, means usually that means it should be at valid all time, basically, as long as you don't have convection. Right? Why you should, I don't quite understand that sentence. Why you need pure scattering? I mean, this is
so what I mean,
radiative equilibrium just means energy balance, so it should always be satisfied as long as you have time-independent, non-convective atmosphere. Right? So why do you need that?
Not really. So
maybe you mean different things. Maybe
yes, I do mean
the terminology is different. This is not what we usually learn in teach body enlightenment.
So if you take the first law of thermodynamics in the full fluid form with the material derivative, and you make the approximation as 1D and you have no fluid motion, you end up with this relationship between the gradient of the net flux and the rate of change of time of the temperature. And this is what I mean by radiative equilibrium. So what I mean is that when the gradient of flux in each layer in the atmosphere goes to zero, the temperature stops changing.
Correct.
Yes,
That
but
part is correct.
What's in the pure scattering?
It's
Why do
not
you need a
about
pure
only
scattering?
pure scattering.
I don't understand why you need pure scattering. I mean, maybe.
what's the objection? I don't understand.
That even if you had absorption, that would still be in radiative equilibrium.
Could be.
Could be.
You're saying that the condition could be satisfied.
Yes.
Right. All I'm telling you is that in the paper in '89, you can write down an analytical solution for this, and it depends on the single scattering albedo, and you can choose whatever value you want. And what these guys have chosen in the '89 paper is they chosen it to be 1, and then they force it to be 0 to get the value, to get this condition to come out.
But that's independent. I mean, that is a separate statement than system is in radiative equilibrium in the pure scattering limit. Because you typically have radiative equilibrium even when you have scattering and absorption and emission.
I disagree, because you can show that global energy conservation, meaning energy into the atmosphere in equals to energy out, that's global. You can show that you can have global conservation and not local conservation. So I can construct an atmosphere for you that's not in radiative equilibrium, but it obeys global energy conservation. I can do that.
Correct, but it is not true that only in the pure scattering limit you're going to have radiative equilibrium.
That's not what it's saying. It's saying that in the pure scattering limit, I would like to enforce radiative equilibrium to inform myself what's the relationship between the Eddington coefficients. That's not what I'm saying.
What if it's not pure scattering? Sorry, we can talk more.
I think we should.
There's some terminology issue.
Let's see the punchline, yeah.
Okay, so when you run through the two stream, before I tell you about the generalized solutions, let's tell you about the plain vanilla solutions, right? So in the beginning of the talk, I told you that I would like expressions that can allow me to transfer flux from one layer to next and back. So if you grind through the algebra, what you get is you get a pair of expressions where the flux going up from this layer, from layer 1 to layer 2, and from layer 2 back to layer 1. And it looks complicated, but it depends on a bunch of, the point is that it depends on a bunch of dimensionless numbers that depend on the strength of scattering. So these are the dimensionless numbers that I call the coupling coefficients. And this curly T is the transparency or the opaqueness of a layer. It's between 0 and 1, right? So once I have these expressions, it allows me to transfer flux between an arbitrary pair of layers and solve the radiative transfer equation. So I would like to talk about generalizing these solutions now. Sorry it took so long to get there. So I would like to concentrate, I would like to forget about black body emission, and I would like to concentrate on transmission and reflection of flux through a layer. So in the two-stream solution, as I've written it, these are the expressions. So this is transmission, and this is reflection, and it depends on three dimensionless numbers like I mentioned. This is a number between 0 and 1. Hidden in this number are the complexities of the chemistry and the opacities that depend on temperature and pressure and so on. But the point is that if it's 0, the layer is opaque, and if it's 1, the layer is transparent. And these zeta plus and minuses describe how absorbing or scattering you are. These are called coupling coefficients. And it looks like this. So they depend on the single scattering albedo, and they depend on this parameter G that describes the isotropy of scattering. When G is 0 is isotropic, and when it's 1 is forward scattering. So the idea behind improving the two-stream solution is that in the plain vanilla two-stream solution, this E value is 1. But I was talking about these Eddington coefficients earlier. If you relax the second condition that I talked about, then what happens is that this can be the ratio of the Eddington coefficients. And let's see what different values of this do to the accuracy of the solution. That's the point of the talk. Right? Now, one thing I haven't told you is what the expression for E. So if you work through it, E depends on this bunch of things. The important thing is that it depends on this quantity called small r. And small r is related to the reflectivity of a single layer in the optically thick limit. And you can calculate this. And once you calculate this, you can figure out what E is. This is a whole, this is the whole parameter space in radiative transfer. The nice thing about this problem is that these two parameters, G and omega, are all between 0 and 1. So you can explore the entire parameter space exhaustively, and you can calculate what E is.
So one clarification, this G gives you the shape of the scattering, right?
Yes.
It seems to be just a number.
Yes.
There's a whole function there, but you're boiling it down to one number.
It's the first moment of the scattering phase function.
Yeah, but what do you do for, let us say, electron scattering, which is not isotropic, but it's still symmetric? What would it correspond to in terms of G?
Oh gosh.
Because I think you're talking about forward scattering being preferred, right?
Mm-hmm.
I suspect that this doesn't include ordinary electron scattering.
It doesn't.
Okay, fine.
Because when it comes to neutrals,
Yeah,
you care about
you don't care
isotropic
about it for
forward.
your planetary atmospheres. Okay.
Exactly.
Yeah,
Exactly.
fine.
Exactly.
Right.
So you should think of this is a measure of how reflective a single particle
This one
event
is how forward it is.
and this is how forward it is. So 0 is isotropic and 1 is forward scattering.
But that scattering is possibly similar to electron scattering, the phase function.
Is
right?
it
Yeah.
front
Yeah,
smash?
that's
right.
similar.
It's
It's roughly similar, right?
It's right, it's got, yeah, it's the same name, 1 plus.
But aerosols are.
It's actually a.
Aerosol is very different. Is that true? I don't.
But remember your question, this is really the first moment of the phase function, how it is 0 for
Electron scattering, yeah, because it's the next one.
I mean,
It's the
I
P2.
presume this is its undercycle expansion, right? Of the moment, so that is identically 0 for electron scattering.
I haven't thought about that.
Sure.
So I'll take your word for it. So I finally get to the one I want to show you. So I want to show you this result from the 89 paper. This is an example of a large, you can think of it as a large reflective aerosol, right? It has a single scattering albedo very close to 1. It has an asymmetry parameter that's 0.8, again, very close to 1. It's a large aerosol. This is the reflectivity of the layer as a function of optical depth. So this is transparent and this is opaque, right? So it goes from 0. Something like 3 × 10⁻², and then it asymptotes at some value. And this was calculated using the brute force discrete ordinate methods, right? So you take this, in this paper, this is taken as the ground truth. And now what they would like to compare is they would like to compare the ground truth versus different techniques and calculate what the error is. So shown here are 3 different techniques. This is the delta Eddington. Delta Eddington was designed to where you put a, remember I told you, you put a delta function in the scattering phase function to deal with strongly peak scattering, right? And the delta hemispheric 2-stream is a combination of the regular 2-stream with this delta treatment. The 2-stream source function is what I described earlier in the talk, which is a hybrid between the solving the equation directly and inserting the 2-stream solution into the integral term. And these are the different errors. So the delta Eddington starts out with an error of around 30% in the optically thin limit and goes down to about just over 1% in the optically thick limit. But what is important is the error at roughly optical depth 1, because if you go back to the basics of radiative transfer, most of the action happens at optical depth roughly 1. So at optical depth roughly 1, for a single layer, the delta Eddington has an error that's surprisingly large. It's about 20%. The delta hemispheric does quite well. It's about between 2 and 3%. And the 2-stream source function approach has an error that is just below 10%. Right? The conclusion from this, at least in this case study, is that the errors are between 1 and 10%. What happens if I use the improved method I told you about, where I let E not be 1? So this is the same plot, just to show you that we could reproduce the results in the previous plot. It's exactly the same setup. Now we use a 32-stream discrete ordinate calculation. So this is the ground truth. This is again delta Eddington and the different methods. And the solid curve is our method. So this is a 2-stream method. This 2-stream method in this particular case is performing better than the 16-stream method by a non-negligible factor. Right? And the nice thing is, the thing to keep in mind is that in this 16-stream method, what you're doing is you're calculating numerically 16 different streams in the atmosphere and you're adding it up to get the flux. Whereas for the 2-stream calculation, you're integrating analytically to get the flux. So the effort is much less, but you get an answer that's much more accurate in this case. But is this true in general? So here is a plot in which we did a suite of radiative transfer calculations through different layers. This is the single scattering albedo, this is the symmetry parameter, this is the optical depth, and this is the error of our method compared to a 32-stream calculation. You can see in the optically thick limit, the error is better than 1%, it's about 0.01% at optical depth 10. At optical depth 3, it's still pretty blue, it's close to 0.01. And at optical depth 1, you get typically errors of about 1%. These these structures that look like caustics that you see are because when you have the ground truth, and let me just draw it. So this is the reflectivity, and this is the optical depth, and this is the ground truth. So what happens when you calculate your approximate method is that some of the methods do this. So they cross the curve at some point. Of course, numerically, it doesn't actually exactly cross the curve. And exactly at the point where you almost cross the curve, you have these dips in the curve. So it's like an optical illusion. And these dips translate in this parameter space to things that look like caustics. It essentially results from either dividing or multiplying by a very small number.
I'm just a little bit confused about how you're defining your error in the previous slide. So you're benchmarking against the 32 stream.
That's right.
In all cases.
That's right.
And you're saying that the 16 stream does worse compared to the 32 stream than your improved 2 stream.
This is 32 stream discrete ordinates, and that's 16 stream 2 stream source function. It's a different method.
So the error that you're plotting on the right axis
Right.
is these two compared to the 32 actual ray tracing.
The flux that results from the 32 stream, yes. So you calculate your 32 streams, you weigh it by the cosine, and you sum it up, and you get flux. So this other plot shows you the error from our improved 2-stream method divided by the error from the 16-stream method that's used very commonly in at least our literature. And you can, again, these caustics are because you're either multiplying by a very small number or dividing by a very small number. But if you ignore these things that look like caustics, it looks pretty blue. So the improvement is between 1 to 2 orders of magnitude. So far, this is a little bit abstract, I know. Let's apply it to a situation where it seems a bit more real. So let's apply it to CO2 ice particles, and I'll tell you in a moment why this is interesting. So the microscopic properties of the CO2 ice particles look like this. So the single scattering albedo is 1 a lot of the way, because CO2 ice has this almost pathological behavior that it is a very weak absorber and a very good scatterer. And at wavelengths where the size of the particle, this is basic scattering theory, where the size of the particle is larger than the wavelength, you're very close to 1. In fact, it's 2 pi multiplied by this, larger than the wavelength, where you're very close to 1. And as the particle starts to be radiatively small, it drops off. So these are different sizes of particles. Now let's take these properties and fold it into a single atmospheric layer. So this is the calculation for a single atmospheric layer. And we have assumed made some assumptions about the size distribution of the particles. It's not so important, but they're large compared to the wavelengths you're looking at. That's what's important. And these are the reflectivity of a single layer for optical depths 1, 5, and 10. So the ground truth in this case is, again, the 32 stream calculation in blue. The improved calculation, the calculation using our improved method is in red, and you can see they overlap very strongly. This Fortney Marley method is in yellow, and you can see it sits above what the ground truth is, and this is the regular 2-stream. And these are the errors as a function of wavelength weighted by a black body function. And the errors in the 2-stream in just one layer, you can see, go from 5% to 15%. Using this Fortney-Marley method is between, it hovers around 5%. And if you use this improved method we told you about, it sits 1% or lower. So the reason why people cared about this was, usually you start the talk with the motivation. I've ended the talk with the motivation. So this is the motivation. There's a body of evidence and a body of literature that suggests that early Mars had liquid surface water. And this is challenging to explain because of the faint young sun problem as well. So during the time we thought this was happening, and this is something I will not talk about in this talk, we thought that the luminosity of the sun was reduced by 25%. So you need an explanation to come up with a climate that can produce this on early Mars. that you can have liquid water at the surface. This paper, which is very influential in the field, suggests that you could have CO2 ice clouds that do something called the scattering greenhouse effect. So the infrared radiation that's trying to escape the atmosphere gets scattered back into the atmosphere, and this has a warming effect that depends on the optical depth of the cloud, how much CO2 atmosphere there is, and how large the cloud particles are. So they found scenarios in which when the optical depth is about 10 and the particles are large enough, you could have early Mars having temperatures that could harbor liquid surface liquid water. So this result stood for about 20 years. Then one of my postdocs came along and said, let's take a closer look. So my postdoc took the same setup, and instead of using the two-stream, he used the discrete ordinate methods, the brute force method I told you about. And he calculated this for a large parameter space. And he found that under no scenario could you produce a surface temperature on early Mars that was above the freezing point of water. So this result essentially overturned the earlier claim that you could use CO2 ice. There are other problems with this explanation, but I think this result was the final nail in the coffin for this explanation. Here's a plot showing you the differences between the two methods. This is the old result, where you have two particle sizes. The vertical axis tells you the temperature difference between a clear sky atmosphere and a cloudy atmosphere, and this is what was obtained in the 97 study. This is what happens when you redo the radiative transfer with a better method, and you get the difference of between 40 and 60 Kelvin, which is a lot on Mars. The surface temperature on Mars is not that high. So 40 to 60 Kelvin essentially changes your conclusion. Now, I would like to end by summarizing the differences between these two methods. So I would like to compare the improved two-stream versus this two-stream source function method. So the two-stream source function method was obtained by calculating a discrete number of intensities and numerically summing over them. The improved two-stream does this analytically, so you get some savings in computational efficiency. The two-stream source function method achieves between 1 and 10% accuracy with 6 to 16 streams. And here we can achieve 1% accuracy in a single layer with two streams. You can use matrix inversion to treat multiple scattering, or you can use iteration. What I mean by that is that we have derived an analytical expression for how to pass flux from one layer to the next for a pair of layers. But in an actual model atmosphere, you don't have just two layers, you have n layers. And now you would like to make sure that the scattering from one of the layers is coupled with the scattering from the other n-1 layers. When you write this out, when you write out all these equations, you will convince yourself that this takes the form of a tridiagonal matrix, which you can then invert. This is what I mean. The other thing that's nice about two-stream is that it's efficient enough that you can include it in three-dimensional climate models. There are hints in the literature that this cannot be done with this method. And because all you are changing is the E factor I told you about, this is trivial to implement if the two-stream method already exists in a climate model. You see, the bias that I came from for planetary atmospheres is that I noticed that this two-stream method was used very widely in these three-dimensional climate models. So we were trying to think of a method where you could use the minimum amount of effort to upgrade all of these three-dimensional calculations. That's why we thought of this. Now I would like to end on the last slide. I'm sorry this is very technical. I was excited about this topic and I didn't want to give you a broad brush overview of exoplanet atmospheres. But in my group, we do a number of things. So in my group, we work on this long-term project called the Exoclimb simulation platform. And we do, we have, for example, spent 3 to 4 years doing a EXO general circulation model, a 3D climate model that we wrote from scratch. And we remove all of the Earth-centric assumptions. We have written codes to calculate opacities. We have written a retrieval code to do the inverse problem. And we've written a radiative transfer code to do the forward problem. And we have also written a chemical kinetics code or for planetary atmospheres. The dream of this is that I feel that going forward in exoplanet atmospheres research, it should be about ideas and not who owns and operates software. And with that, I thank you for your time, and I'll take questions. Thank you.
We already had some discussion, now it's time to continue. Yeah, Ramesh.
So the G, I want to come back to G. So, I mean, it's a number, but the actual scattering is some function of theta, right?
Right.
So in your method, which I didn't actually understand, but you're basically got all these epsilons which you're adjusting depending on G. Does that method just use the number G, or does it use the full scattering function?
It doesn't use the full scattering function. You can think of it as you could always expand that scattering phase function in a large number of terms.
Yes.
And you can think of the G as just the first moment, the first extent.
Right. So then the question is, what is the inaccuracy from the fact that it's not completely described by the first moment? It might have some different shape. So is that included in your error estimates or not?
So yes. So this I didn't explain it very well, I must admit. This delta Eddington method is an expansion of those terms beyond the first term. So in fact, this does worse than this expansion that only keeps the first term. So it has been considered implicitly in this.
Yeah, but the 32 stream discrete, is that using the full function or not?
Yes, that is.
So, yeah, I wanted to ask that specifically too. The 32 stream is sampling correctly at 32 locations, 16 and 16, the full scattering kernel. The angular redistribution function.
We believe so. We believe so. We have tried that, and we have used it. We have used this open source code called Dysort, if you know that.
I don't. And yet, when you're sampling it with 16 locations, or that dotted curve, you're doing worse compared to the first moment of the scattering kernel.
You're talking about the SF8?
Yeah, SF8, or that dotted line, that delta E that you were showing somehow.
So the delta E is just a trick to keep more than one term and approximate the strong forward scattering with a delta function. That's all it's doing, right? The SF8 is 8 streams in each hemisphere, so 16. That's the notation they used. But you should keep in mind that it's not really a 16 stream. It's a hybrid method, right? So it's a hybrid between solving the actual intensity, the equation for the intensity, and using the 2 stream to cheat for the integral.
So what is its G? What's the G that it's assuming? Is it different on the 16 locations?
That's the G.
Right, so it's a number.
It's a number, so okay. It's
That's
a
the G.
number, and
It doesn't use the whole function.
even that doesn't.
That's the G. So I first needed to we first needed to convince ourselves that this was worth doing in one layer with a constant G, right? Then this calculation I showed you is when G is a function. So this is the calculation where we took the full complexity of the G as a function of wavelength, and then we folded it into this calculation, and it still showed that the error properties were superior.
But I think we are worried more about the scattering as a function of theta. It can change with lambda, but how does it depend on theta? And is it okay to summarize it with just one number, which is the first moment?
That's a very good question, and I'm sorry it didn't come across, but that was the entire point of this method.
Okay.
That you don't.
It did come across. I think a number of us in the audience are surprised because that's not our experience. We've done single scattering problems, we've done full kernels versus.
Right.
If we did this in problems relevant to compact objects, for example, we would get the completely wrong answer.
Right, and I wouldn't claim that this would apply generally across all of the astrophysical problems, but
So that's
I'm
why
at
we're
least
surprised. That's all.
that's fine. I was surprised too.
Try to apply this to the Earth's atmosphere?
That's a good question. So in the Earth's atmosphere, this is not so relevant because it turns out that water ice clouds are also very absorbing. So it doesn't really matter till you are very strongly scattering. Whereas CO2 ice clouds have this strange property that they are, see the single scattering albedo is always very close to 1. So the effect is very pronounced for CO2 ice clouds. I would say it would be pronounced in cases where aerosols are very strongly scattering and not so strongly absorbing. And this would involve the silicates that we think we see in hot exoplanet atmospheres. So this would be relevant too. Yes?
I want to ask about those measurements, experimental measurements, omega 0 and G. You take, let's say, in your lab, you take CO ice particles, and what is A effective? Let's say if you do it in the lab.
Okay.
Measure this.
I don't have a satisfactory answer to your question. All I can tell you is that this was done using a me-scattering code, but I do not remember if this was checked against the experiments.
Yeah,
in this particular plot I'm showing you. Right.
Yeah, so the analytical calculation, it can be done for astrophysical dust particles, and they sometimes they don't really agree with the observations. There are clouds that are scattering stellar lights, and sometimes they don't really do good. I don't know if there's experiment actually measuring those.
So you point out a different problem that I feel is important, which is to have a library of validated single scattering albedos and Gs for all kinds of substances. And this is one of the things we are currently doing. We are combing through all the databases. We're trying to figure out which are the ones that are really well characterized and which are the ones where the data is missing. And it turns out that at MIT and Sarah Seeger's group, there's a Simon's postdoc who is measuring this in the lab. So we would like to, determine this and then go to her and say, look, measure this at this temperature. There was another question over there.
Yeah.
Me? Yeah.
So thank you. You point out that where you want to have this high coefficient of scattering, of course, you go to a larger particle size. But when you do that, then the mean free path of the particle seen in now two flowing actual streams of matter, now the viscosity goes way up. And so are you quite sure that in going to a large scattering particle, you have not crossed the Reynolds number and are talking about a scenario in which viscosity has gone up because the scattering coefficient has gone up, and therefore you are in a turbulent regime, which we are in the Earth's atmosphere.
Right, right. I haven't thought about that at all, the change in viscosity, so I don't have an intelligent answer to give
The
you.
opacity is proportional to the diameter of the particle. I'm sorry, diameter squared, the area.
Sure. Sure. Well, I mean, I expect the Reynolds number to be quite high. So
that's the problem.
Right. So if I go from really high to a little bit more than really high, I don't have any intuition what that does.
Yeah. And you can be sure that then the process is not dominated by radiative transfer, which is really all that you've done here, is you sought a radiative transfer solution to the problem of the two-stream atmosphere. And I presume you make reference to the calculation of a viscosity. Can you say about 10 words or 2 sentences about how that calculation works? How do you compute the opacity of a terrestrial atmosphere?
So you go to a database like HyTran. So someone from the HyTran team is sitting at the back. It gives you quantum mechanical numbers for each of the molecules at different wavelengths or wave numbers. So Einstein A coefficient, oscillator strengths, and so on. And then there's a bunch of assumptions that go into like LTE, for example, and you could derive an expression for the integrated line strength, and you make an assumption for the line shape. So let me just write it down. So this is the opacity, and this is the integrated line strength, and this is the line profile, which is assumed to be a void profile. The caveat with this is that we don't have a complete theory of pressure broadening. So everyone in the community has consistently agreed on how we should be wrong. So we cut off the wings of the lines at some arbitrary wave number, because if we let the wings go to infinity, it overestimates the contribution due to pressure broadening. So this is something we all consistently do. I don't think there's any controversy in this expression, besides the fact that it makes assumptions like LTE. And so you could just evaluate this given a spectroscopic line list database like HiTran or HiTem or Exoplanetary. This is how we do it.
Yeah, I just have one quick question about your computational efficiency.
Sure.
So you were saying that you can incorporate this into the global circulatory models.
Right.
And how much time is spent on this radiative transfer calculation, and especially like I presume you have to integrate over a broad spectrum, which have many spectral beams.
Right.
And how do you sort of balance how many beams you choose, and
right.
This two-stream versus you can use less beams, but you use say 32-stream method, which is presumably more reliable.
So let's change this one. So it's really in wave number, and this is your opacity. So what you're saying is that imagine these are my bins.
Yeah.
Within each bin, I have this complicated function that varies over many orders of magnitude,
Yeah.
right?
Yes.
And it could be that you have 10 to the 4 to 10 to the 6 lines. So how do I deal with this in each bin?
Yeah.
There's a method in the Earth and planetary sciences called the K distribution method. So this is one of the things we do. There are other tricks you can do, but the gist of the K distribution method is that there's a theory that allows you to turn this complicated function that is very rich in structure to another function that depends on the dimensionless number that's actually the cumulative distribution, so the area under the curve. So you can take this function in this bin, and now you can sort it from smallest to largest. So it will go look like this. Right? And so now instead of a function that looks very rich, you have a function that's monotonic.
Okay.
You can resample this function using orders of magnitude less points. And there's a theorem that tells you that your transmission, which is this is the column mass. Sorry, so there's a theorem that tells you that instead of integrating this mass, you can integrate this from 0 to 1. So you can turn a function that has, say, 1,000,000 sampling points to a function that has, say, 20 sampling points. The assumption here is that the lines are perfectly correlated. And of course, real lines are not perfectly correlated. So what I mean by that is that spectral lines have different limits, right? There's a limit. Imagine you have CO and H2O. There's a limit in which the positions of the lines exactly coincide, and you know this cannot be true. There's a limit in which they are randomly distributed, and there's a limit in which they completely avoid each other. And this makes the assumption that they are correlated. They have the same line positions, which is not true. So there's an error. But one of the things that in the literature I haven't seen is a more careful quantification of what this error is. So this method is used a lot by different groups, but in the regime of exoplanetary atmospheres, I haven't seen the error being quantified properly.
Okay. So any other questions? So I'm taking Kevin for dinner tonight, so if you are interested, please join us. And also Kevin is here also for tomorrow, and there are still a couple slots left. If you want to meet with Kevin, please sign up. And so let's thank Kevin again.
Yeah. really interesting. Actually, I'll let him go first. So there are many references, but there's no one reference that puts it together. If you look at it together, so I tried to be concise. This is standard astro model, this is the point profile. This is the link to Kevin's schedule. They said it at ITC. I see. Oh, really? Okay. And it was actually invented in stellar atmospheres, but I'm not sure why it was forgotten or abandoned. Taken up by the planetary. Reasons I don't appreciate how there's a paper in which we talk about this.
I didn't track it earlier. Last time I was there, it was
Oh, you have a paper? Oh, okay.
Not only on the face.
Oh, really?
There's a face on it.
I don't remember.
Those are
but
you started with the
oh, you were
I think so, yes.
I understand that. It was very large.
Can I send pictures to
okay. Oh, very good.
You must be changed.
All right.
He sent it to you.
I don't know why. Good to see you.
Okay, so I guess I'm just okay, so as long as Kevin's supposed to be on it every time, maybe we don't shuttle.
Maybe think about it.
I was just trying to beg for how you manage to keep yourself. They were quite. Yeah. For some reason. Oh, it scared me. I can do scared me. Any sort of radiative anyway, you realize this was your turn. Okay. We always have fun.
Yes, okay. Okay.
I see. You know what he's done is very unusual.
You are talking about the state,